Thank you, everybody. Thank you, Joelle. It's true, I have the most gray hair here. I've been around for a long time, and I want to kind of talk about the long view a bit. Actually, so this is the challenge. First, let me say, though, it's really exciting just to talk to all you young people learning about the field, want to get into AI and reinforcement learning. And it's just like, it's a special opportunity. I really appreciate it. And so when I do this, I have to think of what can I try to communicate to you, because you know, we have really a brief amount of time, and the field is immense. I've written a whole book on the subject, and so what can I try to do? Now, my topic nominally today is temporal difference learning, and certainly I'm going to talk about that. But I also want to, you know, just speak to you as young people entering the field, and just tell you the way I think about it from a sort of a longer view. And well, so I think the first thing to be said along those lines is that this is a really special time, and we can look forward now to doing an amazing thing, which is maybe understanding the way the mind works, the way intelligence works. This is like a monumental event, not just, you know, this century, you know, for thousands of years, maybe in the history of the Earth, when intelligent beings, animals, things that can replicate themselves, finally come to understand the way they work well enough to, by design, create intelligence. And so the big thing that's going to happen is that we're going to come to understand how the mind works, how intelligence can work, how it does work, and just the fact of our understanding it is going to change the world. It's going to change, obviously there'll be lots of applications, but just it'll change ourselves, our view of ourselves, what we do, what we play with, what we work at, everything. It's a big event. It's a big event. And we should keep that in mind. And as I say, you know, I'm not saying it's going to happen, you know, tomorrow. It's not, but you know, 10 years it could happen, 30 years it could happen, and in the great sweep of history, that's a small amount of time. It's going to happen within your lives with high probability. So the first thing we have to ask is, why is this happening? And I think it really comes down to like Moore's law. Okay, so I took a slide from Kurzweil. This is his standard slide of the increasing computation per dollar, and it's just reaching a point where it starts to compete with the computation that we can do with our own brains, with natural systems. Okay, that's happening now, and it's just going to continue increasing dramatically. I'm sure you've seen these kind of slides. Here we have time, years along the bottom, and on the other we have computations per second per dollar. Okay, and you see it's a log scale, so of course a straight line would be exponential increase, and Kurzweil argues that it's actually slightly super exponential. But the point is, the computations become available to us, has become enormous, and that changes things. It's the rise of deep learning, and all that is purely because of GPUs and computation getting cheaper. And that will only continue, and it will become more extreme as vastly increased computation. So that alters everything, and it really is profound. And I'm just going to try on a slide to say what I conclude from this, as I think it's an answer to like a question for AI that's had for 60, 70 years. Okay, so the answer, I'm just going to do a couple slides like this, but I guess I should, one last bit of preface is that my talk today is going to be like half, you know, these big things. Okay, and like I'm starting to do now, and half like really small things where you go back to the foundations, real stuff that's basic that we need to understand. Okay, I think the details, the big picture is important, but the details also really matter. And like we heard a lot of specific algorithms early today, exactly how they work is really important. The details matter, but the big picture matters. And sometimes we lose sight of the big picture. Sometimes something becomes so obvious that we overlook it. I think the computation is along that lines, and its implication in a phrase is that methods that scale with computation are the future of AI. Okay, and that's that's by scale of computation, I mean as we get more computer power, those methods become more powerful. And this has not always been true. But certainly it's true of learning and search methods. These are what we call general purpose methods. And it's the answer to this, one of the oldest questions in AI. For 60 years old, do we want weak methods? That's what they call them. In the old days, they called general purpose methods weak because they just use the data or use computation. They can only, they're general purpose. They're general, they're weak. Okay, that's what they called them in the old days. The strong ones were the ones that would lose human knowledge and human expertise and human insight to make their systems so much better. Okay? Now, probably you guys are thinking that's crazy. The general purpose ones. Are you thinking that with me? General purpose? How many of you like to go human insight? Oh, some of both? Okay. Yeah. That's a nice compromising sort of position. And so all today I'm going to try, or all in this big part of the talk, I'm going to try to talk about, I'm going to present strong views, okay? Really, maybe you should do compromises and nuances, but it's good to talk about strong views because they give you a working hypothesis, they give you a point of view, and you can say, this is a strong point of view. You don't have to believe it. You have to say, well, that's a strong point of view that I should be thinking about. And then maybe you have several of them. Anyway, so I'm going to present the strong point of view that this oldest question has been answered, and it's been answered in favor of the weak methods. Yeah, and now I don't want you to, I could talk about this all day, but I'll refrain from it. I'll just note the next thing to say is that you're thinking you're good. You're thinking you're into deep learning or reinforcement learning, so you're on the right side of history. But I'm not sure that's right, okay? Because we take things like any kind of supervised learning, even model-free reinforcement learning, the thing I love more than anything, right? It's only weakly scalable. If I had, a million times its computation, I'm still limited in my model-free reinforcement learning by how fast I can gather data. And, I'm only learning a value function, maybe a policy. What's the big deal? It's a tiny object. It's some map from states to what to do. Okay, and that's not a big thing. I don't care how many features you have. Certainly for supervised learning is only weakly scalable because it requires people to provide data sets, okay? And they become the bottleneck. If you have, you get people to label things on the web, things scale, but only weakly. Only as fast as you can gather the data. And eventually that becomes a bottleneck. You really want to be able to learn from raw data. You want to be scalable, okay? So if these things that we love are not scalable, what is scalable? What would be fully scalable? Well, my answer is simple. It's what I call prediction learning. Prediction learning means learning to predict what will happen, okay? And so it's the unsupervised supervised learning because we have targets. With supervised learning, we just wait and we see what does happen, and that's our target, okay? And so you don't need to have human labeling, or you have a target, but you don't need a human to provide it. You just get it from the data. So it's the unsupervised supervised learning. But anyway, it's definitely the scalable model-free learning, and maybe it's the scalable model-free learning. Prediction learning is at the heart of all of our control methods where we learn value functions. I think maybe that's sort of the argument the big argument about temporal difference learning is that it's the scalable model-free method. And of course, I haven't given you even a step towards that yet. I'm just saying that the idea of predicting, of having learning that predicts is the key problem. It's what we should be thinking about. And you may say, well, deep learning, supervised learning is all about prediction learning, but that's not true. It's about predicting what the label will be, but it's not about predicting over time. It's not about predicting where you have to wait and see what happens. And that makes all the difference. Okay, so with all this words, I want to ground us a little bit and remind us what the data looks like. So I put in this slide of this is what real life is like. Real life is a temporal stream. We have things like we're playing soccer and we have to make actions at every moment. We're maybe a hyena being chased by a lion and it's trying to predict whether it's going to live or die. We're maybe a baseball player and our eyes are watching this tiny little ball flash by us really fast. I have to swing at just the right moment to hit the ball. Or maybe you're talking to someone, you're trying to predict what they will do. So this is the data streams that AI should be learning to deal with. And so we should always keep this in mind. When I say learning to predict, well, I do think of that like a hyena trying to predict, fear. Fear is your prediction of are you going to die. Okay, so he's trying to predict it. Several times it looks good and bad. And at the end here, it's not looking so good. Okay, so with those prefaces, let me start talking about temporal difference learning. Temporal difference learning. Temporal difference learning, it's a method for learning to predict. It's widely used in reinforcement learning to predict future reward, value functions. And it's basically the center, the core of many methods that you know about, Q-learning and SARSA, TD Lambda, deep Q networks, TD Gammon, the world champion backgammon player, using deep reinforcement learning from 25 years ago. My God, 25 years ago. Deep reinforcement learning, 1992. But not all reinforcement learning methods. So AlphaGo, it happens not to use TD learning, uses other kinds of reinforcement learning. The helicopter thing that you might have heard, that doesn't use it. And then there's sort of pure, Peter's talk was interesting because he talked about policy-based methods, and some of those don't use temporal difference learning, but eventually he would get to it and put it in to make things better. So it's sort of, yeah. So it's sort of optional. It feels like it's optional. Many people will say it's optional, but I do want to argue that you do want to use it. That really you should always be using it. It's ubiquitous. And okay, it seems to me how the brain works. What else today? Oh, now it can be used to predict anything. It's for general method for prediction learning, not just for rewards. Okay? So don't be fooled by, in reinforcement learning, you read all about TD, it's all about predicting value functions and reward. But we can use it for anything. And since my talk is just about TD, I want to be sure to think about this general use. Question?
Not saying that it's key to AlphaGo, but don't they use TD learning to train value functions that they use to evaluate states at the end of the research instead of searching?
Yeah, I've forgotten exactly the details. The initial learning system was learned from actual outcomes, actual games, and they would go all the way to the final outcome. They would make a prediction, look at a position, make a prediction of how am I going to win or lose, and they would go ahead and see who actually won the game at the end. And they would use who actually won instead of a temporal difference learning. So that's what we want to work for. Do they wait and see who actually won? Do they see the outcome or the return? Or do they update it a guess from a guess? Okay, let me make that clear. So that's my next slide. Is the TD learning, what is TD learning? Well, basically, it's learning a prediction from another later prediction. Okay, so if AlphaGo was looking at a position, making a prediction, and then zooming all the way to the end of the game and see who won, and then it's not TD. It's not learning that prediction from a prediction. On the other hand, if you make a prediction from a position, and then you make one move, and you see your next prediction, and you use that next prediction to form a target, then you're doing TD learning. Okay? So the quick phrase is we are learning a guess from a guess. Okay? Sounds a bit dangerous, doesn't it? What would constrain it? What would tie it down? Okay, but that is the idea. We want to learn an estimate from an estimate. And we have to talk about whether this is good or not. Okay? The TD error is the difference between two predictions, two temporally successive predictions, right? So if you're playing your game, you say, I think I'm winning, and then you take another move, and no, now I think I'm losing. You try to learn from that. You don't know who actually is going to win, not yet. But you try to learn from the temporal difference in your predictions. Okay? Now, after that, it's the same as what you're all used to. You just have an error and you send it back, prop it through, or whatever you're doing, And so it's just really, where does the error come from? Or where does the target come from? Does the target come from the end of the game, or does the target come from the next prediction? Okay, so here's the example of T.D. Gammon, originally 1992, and he had a backgammon position, he would send that into a neural network, which would filter through actually just a single, well, he had many versions. The standard version was a single hidden layer, and he'd end up with this probability of winning. And the error then was the probability of winning in one position minus the probability of winning in the next position. So we look at the change in the estimated probability of winning, and that was used as the error that would be backpropagated through it. And this would learn, just stick it in a corner, playing against itself, learning from itself, from its own trial and error. And it came out to be competitive with the world's best players, really the best in the world. Okay, so that's familiar. Now, I'm trying to get to this question. This question is, do you need to use TD learning? Because all this is to motivate. The motivation is the most important. Do I need to use TD learning, or can I get away with it? Because if you go to the field now, maybe even in reinforcement learning, you'll find a good fraction of the people don't believe in TD learning. They think they can get away without it. Okay, and so it's a real question we should all be asking. Do we need it? Or I want you to understand, I want you, even as people learning about the field, to be able to engage with this question and know the basic facts pertinent to whether we need to use TD learning. Okay, so I will skip over Atari. And because you've seen that already. So TD learning, when do we need it? Okay, well, it's only relevant on multi-step prediction problems. That's the first thing. Only when the thing predicted is multiple steps in the future. So obviously, if you're predicting the outcome of a game, that's multiple steps in the future. But if you're predicting a label, or in AlphaGo, where the initial data at least was, here's a guess, and then I'll just see who won the game. And if you just use who won the game, then it's essentially a one-step prediction. Okay? Okay, so now I want to say that it's really broadly applicable. I've said it's only applicable when you have multi-step predictions, but really everything you want to do is going to be multi-step prediction. If you want to predict, I have some examples. Multi-step prediction. If you want to predict the outcome of a game, if you want to predict what a stock market index will be, well, really, you could just predict what it's going to be, but you'll get more data on every day after that, and you'll make new predictions. So you'll make repeated predictions about a long-term outcome. If you want to predict who'll be the next president, you can predict that, every day as a new event happens. If you want to predict who the U.S. will go to war against next. So all these are long-term predictions. They don't jump to the end. Now, even if you want to predict a sensory observation, if you want to predict just the very next sensory observation, that would not be multi-step prediction. But if you were to predict, even 10 steps ahead, or a discounted measure of the future, those are long-term or multi-step predictions. And we go back to the real world, the hyena and the lions, or the conversation, or Messi playing soccer. He's got to make long-term predictions. It's not, what's the next thing? It's, am I going to make this goal? Will I get around that fellow? Where's the ball going to be in a few milliseconds from now? All these things are multi-step predictions. Now, can we treat it? Can we just use our one-step methods? Like, sure, things happen bit by bit, but ignore that. Just wait and see what happens. Like see who won the game and use our one-step methods. And, or can you learn a one-step model and then compose your model? Okay? And the answer is that we really can't do these things. And I want to try to give some sense of that today. I'm really going to talk mainly about this first question. Can we think of the multi-step case as one big step, or do we have to deal with it bit by bit? But I want to do one slide on the second bit. The second bit is, can we learn one-step predictions like a model and then iterate them to get a multi-step prediction when you need to? And I just want to say that I think it's a trap. Okay, and I don't know if I can really properly explain this to you, but I think it's a trap. I think it's enough to model the world to make like a low-level simulation of the world, to make like treat the world as a Markov decision process and model the transition probabilities, or treat the world as a engineering model where we just have to learn the velocities and the effect on the accelerations of our actions, and then integrate this low-level differential equation. This is all a trap. These short-term models and then iteration it feels good because we know that if it can be done perfectly on the one step, then it can be done perfectly for however far we want to look into the future. But there's two problems. First of all, we can't do it perfectly. And when we do it imperfectly, because we're always going to have an approximation, then when we try to iterate them, we get a propagation of errors, a compounding of our errors, and we get a useless long-term prediction. And secondly, of course, it's exponentially complex. Because as we look ahead, each step, there will be many possibilities. The world is stochastic, and also our actions, maybe we have different choices we might want to look at for our actions. So it quickly becomes computationally intractable. And it will always be computationally intractable to try to look ahead many small steps into the future, like to try to iterate your model of physics to get to, how much fun will I have going to Montreal and taking the summer school, okay? It's crazy. And it just there's no future in that way of thinking. It's a trap, and lots of people in my opinion, are falling into it. Okay, but let's go back to the other side. The other side, remember, I'm just going backwards here. We have these two ways to get away from TD if we don't want to get away, if we don't like TD. Can we learn a model and iterate it? That's the second one. Or the first one, can we think of it as a one-step thing and just do the one-step thing? Okay, so the one-step thing, I'm going to do it I'm about to transition to my low-level part of the talk, but I don't want to try to answer it here. Just at the high level, and then maybe we can even take questions after this high-level part of the talk. Can't we just use our familiar one-step supervised learning method? And in reinforcement learning, these are known as Monte Carlo methods. I mean, you just roll it out or whatever, see what happens, and use what happens as a target. Okay, so this has costs. Number one cost is you're making this prediction, then you're rolling it out to the end. And really, you're going to make a prediction at every moment in time. So you've got to remember a whole mess of predictions as you go out to the end to see the outcome. Or really, if you have returns, you get the outcomes at different steps, different outcomes. And you have to relate them back to the earlier situations. It's horribly complex. It's nasty. Okay, first of all, you need to remember all the things you did. Think about yourself. Maybe you're the lion there. You're trying to make a good prediction. Okay, and what do you have? You have all this stuff swirling around you. You have the hyenas running away. You have a glimpse of him. Your feeling of your feet. You have all this stuff that you can sense, and then you want to relate that to how well it's going, how good you should feel about this chase. Okay, and so what? Is it sensible to think, or it would just be much better if you could do it now? If right now, when all this stuff is in your mind and in your sensors, learn if it's going well or going poorly, and learn now, as opposed to wait 5 seconds later when you have had a whole large number of frames of different sensations, different patterns of sensation. You've forgotten. If you have to wait 5 seconds till the end of it, it's too late. You can't remember all that. Whatever you remembered will be a tiny shadow of the real vivid representation you had at the time it happened. Okay, and of course the computation is poorly distributed. You can't learn now. So what are you doing now? Later you'll find an outcome. You'll have to do all the learning then. Just a poor temporal distribution. And you can avoid these problems with special methods, and that's really what TD is about, specialized method for the multi-step case. Another reason that you don't want to wait is that sometimes you never know the target. Like, I don't know, let's say you're playing your chess game and there's a fire alarm and you never finish your game. So you never see a final outcome. But if you're TD, maybe you thought you were winning and then, it was going really poorly. And so you did something bad. You can learn without waiting till you're checkmated. Maybe the fire alarm just like one move away from the checkmate. So technically the game never ended. And, but you can learn a lot from your experience. So now we could try to ignore all these things, think of them as nuisances, but I think of them as clues. These are hints from nature about how we should proceed. Okay. Okay, so now I'm going to get down to it more technically. But I hope you're starting to see the view I'm trying to present. We really need to learn from new predictions so that we can do it as we go along. I think it's really ubiquitous in all the different kinds of learning we're looking at in AI. Okay, so I'm going to use notations a little bit different than what we've heard earlier today. It's what I call my new notation. I use it in the second edition of the reinforcement learning textbook. The big thing is that we're trying to use the statistician's convention that random variables are capital letters and instances are lowercase letters. So all of the things that happen that make up life are capital letters, right? Because they're the random events that have actually happened. They're not possibilities, they're whatever happened. So S0 is the first state. A0 is the first action taken in that state. R1 is the first reward that depends on that state and taking that action in that state. And then at the same time as we get the reward, we get the new state. So I like to give them the same temporal index. R1 and S1, they occur together. They're jointly determined, in fact. Okay, and then life goes on, and that's the data. That's all we have in terms of data. We have trajectories and maybe a single trajectory. And we're interested classically in the return, and the return is a sum of rewards. And I'm not going to use capital R for the return because capital R is actually the actual rewards, the sequence of rewards. And so I'm going to define the return. I need a new letter. I'm calling it G, capital G, because it's a random event. Whatever sum of rewards after time t actually was, we're going to call that G of t. G of t is the return. And as we note here, if I can use this thing, this dot just means that this is a definition. It's not a statement of something that's true because it follows from other things that I've said. It's a definition. So G of t, the return, is the sum of the future rewards with the discount rate is the most common way of dealing with it. And that, of course, can be written, now we're going to use equality because it's not a definition. That equals the first reward plus gamma times the sum of all the later rewards. We're just taking one factor of gamma out of all of these guys. So this is no gammas. This one is one gamma. Now this guy is two gammas. We just take the one out. And then the rest of this is the sum of future rewards from one time step later. Okay, so it's a bit like what we started with. It's just like the same thing. It's G of t plus 1. Okay, this is just a definite. This is a true equality here. Any return can be written as the first reward plus gamma times the next return. Okay, and that is going to be the basis for our temporal difference learning because we're going to we're basically going to use this is we're going to use this as a target. We're going to use the next reward plus gamma times the next return, essentially as a target. I guess that's going to be explained right next. We look at a state value function. Okay, since we're using capital letters for the random variables, I can't use capital V for the true value function. Okay, it's got to be lowercase, and it's a function of the policy. So V pi of S, where S is any particular state. It's an instance, any state, lowercase s. Its value is the expectation of the random variable, the return, if we started in that state s. Okay? So what we can expect the return could be under pi. Pi is the policy. So it's some way of picking the actions. Of course, the value of state depends on what you do. If you dance at the top of the Grand Canyon, it might be bad. But if you can sedately walk up to the railings, it's good. So policies, values depend on policies. Okay, so then, since this is the return, we can just use the above equation. The return can be written as the first reward plus gamma times the rest of the return. And then since we're taking the expectation of this is the expected next reward, and the expected value of the next state. Okay, so that naturally leads to the notion of an error. We can compare the estimated value of a state at some time to the reward and the estimated value of the next state. Okay, so that's going to be our TD error. This is what we're going to use to replace the normal conventional error. Now this V is a random variable. This is our estimate, and our estimate will depend on what happens, and so that is random. The estimated values are a random value, or a random function, and so it's capital, and that's our TD error. You got it, the TD error? Was that clear? Good. Okay, so now let's talk about our methods. I want to contrast supervised learning, and remember I said supervised learning is called Monte Carlo in this context. So what exactly is that? That's we take our estimated value function for the state that we run into, v of s of t, okay, we're going to update it based upon some experience. Okay, here's the experience. Here we are at s of t, and this is the tree of the things that might happen. Like we might pick either of these two actions, and if we did pick this action, either of these two states might arise. So yeah, the black dots are actions, the open dots are states. So basically, this is the tree of all the futures that might happen, and in this case, we're imagining that there are terminal states. We're basically adding things up until we reach a terminal state. So here is a particular trajectory that might happen. Let's say it did happen. From that state, we went this, and then we terminated. Okay? So we now, once we've terminated, we know what G is. We know what the return is, and we can do this update rule. We can compare our estimate for the state at time t up here to the actual return, and we make that error, and then we do an increment. This is the step size alpha, so this is a number like 0.1. So we increment towards this target. Okay, that's a standard. It would be a Monte Carlo learning rule, a supervised learning rule, and that's the competition for the TD method. The simplest TD method looks instead like this. We only look ahead one step. We're at S of t. We look ahead at 1. We see the reward that happens and the next state that happens. And based on those, we form this TD error, which is again is comparing. We're updating the estimate of this for the state at time t. So we're going to make an error between what we were guessing for that state and this new target. The reward plus gamma times the estimated value of the next state. Okay, now you've probably also heard about dynamic programming. And you can put dynamic programming in the same figure, the same kind of figure. And if you were, the dynamic programming version looks like this, because it's not considering a single line through the possible tree. It's considering all possibilities. It's considering both actions and both possible next states. So this is where you need the model of the world, because although you know you're probably picking each action, the probability that the world will give you possible next states will be known only to the world, but in dynamic programming you assume you know all that. So in dynamic programming the equation is that the value, the estimated value for a state is moved towards the expectation of the first reward and the expectation of gamma times the value of the next state. Okay, so there's this expectation, and that's what makes it dynamic programming, because you assume you know all the probabilities, you can figure out that expectation. It doesn't give you the answer because your value will still be, you're still learning a guess from a guess. You're learning your new estimate still from your old estimate. Well, that's dynamic programming. So really, we can say the following. What's special about TD methods is they bootstrap and sample. So bootstrapping is this idea that your target involves a guess, an existing prediction. Okay, so Monte Carlo, the whole point is that it doesn't bootstrap. It's just looking all the way to the end and seeing what the return is. There's no estimates playing a role in the return. Dynamic programming also bootstraps. Dynamic programming says look ahead one step and look at the expected value of the next state and back it up. So you're using your estimates, and your estimates gradually get better. And TD, of course, also is using your estimate. Yeah, it's like Monte Carlo and TD are learning methods. I guess that's my next point. The learning methods, Monte Carlo and TD, they sample. They sample what happens because you don't know how the world works. And dynamic programming does not sample. It just uses the expectation. It assumes you know what will happen, what could happen. So those are the two basic dimensions, whether you're sampling and therefore learning, and whether you are bootstrapping. You're using you're bootstrapping your estimate from other estimates. You're learning guesses from guesses. And so TD prediction. Basically, I'm just saying this is the update you saw before. We're updating. The Monte Carlo is here and the TD is there. So just the contrast is that one, the target is the actual return, and the other is the target is this sort of one-step estimate of what the return will be. Okay? Now, let's do an example. So here I am, I'm coming home after working a hard day at the office, and I'm trying to guess how long it will take me to get home. Okay? So I'm leaving my office, it's Friday at 6 o'clock, I have some other features, and I make a guess of how long it will take. So I'm going to guess it'll take 30 minutes to get home. Okay, so, and that's my prediction of my total time, because I haven't gone, I'm just starting now, so my elapsed time is 0. Now, as I come out of my building, go to the parking lot, and I see it's raining. Okay, and it's raining. It's going to take me longer because everyone drives slower in the rain. So I think, well, first of all, I've already spent 5 minutes just getting down from my office into the parking lot. And I also think it's going to take me longer. I think it'll take me 35 minutes from now for a total of 40 minutes. Okay? So what I want you to see, the first thing you want to see is that my guess about how long it's going to take me and my guess about the total time to go home, it's constantly changing. As I get more information, I revise my estimates. Okay, so to carry the example through, I start getting my car, I drive on the highway. It turns out it didn't take as long as I thought. I've spent 20 minutes total now, and I think it'll only take me 15 more to go home. It wasn't so bad in the rain, and so that's 35 minutes total. So this column is my total estimate as it goes up and down, and then I get stuck behind a truck on a secondary road, and so I think it's going to take me longer. And then I reach my home street, and I think it'll take me 43 minutes, and it does take me 43 minutes. Okay, so that's a possible thing that might happen, a possible trajectory. And what I want you to ask is what you might learn from that. Okay, so if you're doing a Monte Carlo methods, you just say, well, it took me 43 minutes to get home. That's the answer. So all my estimates, my first initial estimate of 30 minutes, that's going to be moved towards 43 minutes. That's the error. In fact, all of these will be moved up towards 43 minutes, because whatever guess I made at each point in time, it should be moved towards what actually happened, or whatever is remaining in the future at that point. Okay? Now, if you're using a TD method, if you're using your guess, you're going to learn a guess from a guess, then something very different happens. So even some of the signs change. So your first prediction will move up because you started out at 30, and then after you found out it's raining, so you'll move up. But this one, for example, will move down. And all the errors are different. All the errors are different. In the long run, it'll all wash out. But for all actual learning is very different. Okay, now I also want you to think about the computational consequences. Okay, if you're doing TD, then when you're here and you go to the next stage, you get an error, and you can update right away. You can say, well, why did I make that prediction? What are my features there? How shall I change those? What are the contents of my deep network that led me to make that prediction? I need to change those. And that's true at each step. So when you go from here to here, you can update this guy, and then you can forget about it, because you're never going to update him again. Whereas in Monte Carlo, you have to remember why you made each one of these predictions until you get to the end. Then you have to go back and say, well, okay, why did I make that one? And then adjust its weights, with knowledge of its feature vector and the contents of your network. and so on. Yeah, and it's terrible. It's distribution because you keep, all this time you're doing nothing. You're driving home, but you can't do any learning. Okay, you can only wait till the end. You know the answer, and then you can go back and to all the earlier things and learn them. So the distribution of computation is poor. The memory is poor. It's just kind of inconvenient. It's much more convenient if you can do it as you go along. And you think about it. You're in your car. You're trying to drive home. You get stuck behind a truck. Do you say, this is bad? You know, I say, it's going to take me longer than I thought. I was too optimistic before. You don't say, well, you know, maybe this truck will disappear. And you don't say, hold judgment. You could hold judgment until you get home. But, you know, my feeling is I'm learning as I go along and I'm responding to what I see. And we actually do learn as we go along. Okay, so I think I've said these things. In TD with Monte Carlo, you can be fully incremental, learning as you go along. You can learn before you know the final outcome. This means you need less memory and less peak computation. You don't have to do it all at the end. You can even learn if you never find out how long it takes you to actually go home. You know, maybe you get a phone call and you're called away for something important, and you never find out. But you can learn without knowing the final outcome. Now, when you do the math, both of these methods will converge, and so the only question is which is faster. Okay, this is the only question, but it's a big question. Okay, so I don't know. Let's just do a simple experiment and find out. Okay, so here's a trivial experiment. Famous, I don't know. I did this a long time ago. Just a random walk, and it's meant to test the idea of which one of these is better. So we're gonna have 5 states, and we're just gonna have an estimate for each state of what the outcome will be. Okay, this random walk, it takes 50-50 step, right and left, and you start in the middle, and you go back and forth, back and forth, back and forth, until you end at one side. Okay. If you end at this side, you get a 0, and you do get zeros all along the way for your reward. But the only way you get a non-zero is if you end on the right side. You get a reward of 1. Okay? So are you with me? What's the correct prediction? So the correct prediction, there's no discounting here. So we're just trying to predict the sum of the rewards up until the end. What's the correct prediction for the start state C? You're in C. What's the correct prediction for the expected value of your return?
Gamma squared.
Gamma squared. Gamma is 1.
Oh, then 1.
So the expected return. So if you go blah 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 blah, and you end on this side, the return is 1. If you end on the other side, the return has to be 0. So you start in the middle. What do we expect the return to be? Yeah, by symmetry, it's going to be like 0.5. Okay? And state B, I don't know, it's going to be less than 0.5. And state A, still less. Anyone want to guess what they are? The true values of all the states? C is definitely a half. What do you think B is? Guess? Just guess.
A third.
A third. Yeah. I thought it is a third. And the next one is a sixth. Yeah, these just go by sixths. 1 6, 2 6, 3 6, 4 6, 5 6. And those are plotted here. This thin line is supposed to be the true values. So state A truly has a true value that's 1/6, and state B has a true value that's 1/3. This has a true value of 1/2, and so forth. And these other lines are the estimated values from applying TD to it. Okay, so with TD you do have to care about the initial conditions because it's making a guess from a guess, right? So your guesses, affect things. They either pollute things or brilliantly provide good guesses of value. Okay, so the initial guess is 0. So at episode 0, all of the estimated values, all the estimated values are half, because since there could be zeros and ones for possible returns, it seemed reasonable to start the estimated values all at a half. Well, that happens to be right for the middle state, but it's quite a bit wrong for the other states. And then we're going to do episodes, and we're going to learn on every time step, and we're going to update the states according to the TD rule. And after one episode, we have this darker line. This is the episode number. After one episode, we have these values for our estimated values of the 5 states, right? So what do you know happened on the first episode? You ended on this side because, well, what's going to happen? What is this TD rule going to do? What is the TD error going to do? Let's say that we start in the middle and we could go either way, we move around. Well, what's the TD error going to be? It's going to be the reward. The reward at the beginning is going to be 0. And then it's gamma's 1, so we forget about gamma. And then we just basically the change in the value. Okay? And if you went from, say, this state to this state, what's the change in value? 0, because their estimated values are all a half. And so we went from one state, from an estimate of a half, to another state with estimate of a half. So as we go all this bouncing all around, nothing is going to happen, really, until we run into one of the ends. Well, if we could run into this end, or we could run into that end. If we ran into this end, we'll go from a state that was a half to, the terminal state. The terminal state always, by definition, has a value of 0. Okay? So over here, if you did this transition, you get a reward of 1. A reward of 1. The starting state here would be a half, and you get this thing that has 0. Okay? So it'll be 1 minus a half. It'll be positive a half. Anyway, the estimate of state E would go up. And that didn't happen, because here's the estimate of state E, it's still at a half. Instead, what happened is we ended on this side, and we went from here that had estimated value a half to this thing which has estimated value 0, the terminal state. And so we went from a half to 0, and our TD error is minus a half. So we moved down from a half towards 0. And you can actually see how far we moved. We actually moved from a half to 0.45, and so our step size alpha was 1/10. Okay? We can understand this algorithm. It's very simple. And then as you get more episodes, you get closer and closer to the true value. After 10 episodes, you get the blue line. After 100 episodes, you get close to the true values. You never get exactly to the true values, because there's always randomness in the individual episode, and alpha is non-zero, it's a 10th, and so you keep bubbling around the true values. So that's an example. Now, let's compare now Monte Carlo versus TD on this problem. Okay, and we have to draw whole learning curves now, and we have to worry about what's the value of the step size. Okay, so what I'm showing you in this is a learning curve, meaning the x-axis is time, or episode number, and the y-axis is some measure of error. It's actually the root mean square error averaged over the 5 states, and many iterations of the whole experiment. I guess 100 iterations of the whole experiment. Okay, so as I said, they're going down. Everything's getting better over time, but things will not go to 0 because, well, we have the step size, 1/10, or whatever our step size is. It's always going to be there, and we're always going to have some residual error. I don't know, which one should we look at first? Maybe Monte Carlo. It's simpler. Monte Carlo, you just wait until you know what the final return is, and then you do your update for all the states that were visited. So if you take a nice slow learning rate, 1/100th, we just gradually move down towards 0 error. And it's actually, this alpha equals 1/100th. They're very slow. We'll actually get the closest in the long, long, long run to 0 error. But it's very slow, so you might want to go faster. If we take alpha as 1/50th, we go down faster, but we're going to start to bubble. And we tried going as fast as 0.04, and we do go, the initial part is fastest, but now we're definitely bubbling. And you can't really do better. There's no step size which will do better than the ones that are shown here. If you try to go faster, you're going to, you may be a little bit fast at the very beginning, but you're going to level out at a higher level. Okay? And for TD, we see a similar pattern, but all the numbers are lower. Okay, so here's our one, the slowest one I'm showing here is 0.05, and it goes, it's slowest, but it gets slower. And then other ones are faster, and of course they bubble more, and they don't get as low in the long run. Okay, now if we have someone may ask you, some of you may be wondering, what's going on with that TD stuff? Because it seems like they go down and they start to come up again. Is anybody wondering that? Anybody wondering that? Yeah, it's weird, isn't it? It's real. It's not a bug in my program. That's the first thing to be sure of. Yeah, it has to do with the fact that actually starting out the estimates at a half is not stupid. It's actually a reasonable guess. If you started all the estimates out at something really bad, then you wouldn't see that bounce. I call it a bounce because we go down and then we seem to bounce and we come up a little bit higher. And that bounce is really interesting. It has to do with the fact that we do have some effect of the initial estimates in TD, and whereas we don't really, at least not as much for Monte Carlo. Okay, so this is just a random walk, and I've been systematic about the random walk, and I don't know, the big picture is that TD is faster, okay? There's a bounce, okay, whatever, but it's still much faster. But this is just one problem. This is just a random walk, okay? Maybe it's something special about the random walk. Or maybe if I did it on, Atari games, I would get a more fundamental result. Now, I like to do simple things. Question?
Yeah, so the thing that you showed, it means that it doesn't converge?
Oh, no, they all converge. Even with a non-zero, if you don't reduce the step size, then you don't expect anything to converge, right? They would converge in the mean, okay? And all of them will converge to a mean that depends on the step size, and higher step sizes would be higher, and lower step size would be lower. Convergence point, yeah. The convergence properties are roughly the same in both cases. I want to ask now, can I say anything about the general case, not for the random walk? But can I say general case? Actually, no. I'm going to do that in a minute. But first, I'm going to do the random walk again under this setting that I call batch updating. Okay? Batch updating means we take some training set, like 100 episodes or 10 episodes or whatever, and we present it over and over again until it does converge. So even for a finite step size, we'll get complete convergence if we repeatedly present the same training set. Okay? Because there's no randomness in random samples, you're just bringing the same data over and over again, and you will converge. The two methods, TD and Monte Carlo, will converge to two different things. And this is for constant alpha. These diagrams converge to different things. As long as your step size is small enough, it won't depend on your step size. Yeah, all step sizes, as long as they're small enough so that you don't diverge, will converge to the same thing. Okay, and they converge to different things. The two algorithms converge to different things. So we can ask on this problem, which one converges to a better thing if we present the data over and over again to the algorithm. Okay, and here's the results on the random walk again. We have different numbers of different sizes of our training sets. We're increasing that along here, but for in each case, say with a training set of 50 episodes, we present those 50 over and over and over again until we converge, and we measure the asymptotic error that is independent now of the step size. So I can now eliminate the effect of the step size, just going to measure which algorithm is getting me a better result on this problem. Okay? And TD is faster by this measure. I mean, we're doing a lot more computation. We have to go to convergence. We have to repeatedly present things, none of which I like. But it's getting us insight into what the real difference between the two algorithms. So it's like TD is moving towards a better place, even on a single example, as suggested by the initial results. And if you go over and over again, you can get that. Okay, now this again is all random walk, and you have to ask if this happens on all problems. So one approach would be to do all problems, and that's obviously not satisfactory. So what can you do instead? You can try to prove a theorem, okay? And you can also try to get insight. I guess I'm going to try to get insight first, and then we'll do the formal result. So let's try to get insight into us as people. I want you to be the predictor. Imagine you were having some experience. So imagine you were experiencing a training set of these eight episodes. These are all very short episodes, right? So most of them are episodes like B0 means I'm in state B, and then I get a reward of 0, and the end of the episode, that's the end of the episode. Okay? Or I see state B, I get a reward of 1, and that's the end of the episode. The only non-trivial episode is this first one, where I'm in state A, I get a 0, and then I go to state B, and for B I get a reward of 0, and that's the end of the episode. Okay? So that's the data you see, just these 8 episodes. And I want you to tell me what prediction would you make. Okay? The first question is, what prediction would you make for state B? If you found yourself in state B, what would you guess for the expected return ahead of you from state B? Say again? 3/4. I agree, because how do we do that? We said, well, I was in state B all 8 times, and 6 of them ended up with a 1, and 2 of them ended up with a 0. So you're going to guess 3/4. Okay? Okay, that was an easy one. What about state A? State A, it's really much more uncertain. We've only been in state A once. And what are we going to ask for state A? Just take a moment and think about it. What are you going to guess the return if you find yourself again in state A? What is the estimated value? What would you estimate the value of state A as? Okay, now, I'm going to say right away that this is a question there's multiple good answers to. Okay? So I'd just like someone to raise their hand and give me one answer and why it's a good answer. Okay? How about you?
75%, because you always go from A to B. So if you always go from A to B, and B is 75%, so you get 75%.
If you always go from A to B, and the only time we've seen A, we went from A to B, and B has value 75%, 3/4, then A should also. That sort of makes sense. What's another good answer?
0, because every time that A occurs, the reward is 0.
Yeah, I don't know if everyone heard that. You said you've seen A once, every time you saw it, the return was 0. And so, why not predict 0? Okay? Now those two answers are the Monte Carlo's answers and TD's answers. Okay, so we could say 0. That's what Monte Carlo would say. Monte Carlo just looks at what happened. I was in A once, and the outcome was 0. So I should predict 0. Monte Carlo. Now the other one is what TD predicts. It's also what you would predict, and this is the gentleman explained what was going on in his head. He was saying, well, I'd seen A go to B, and all that sort of stuff. He was building in his head this model. He was saying, the only time I've seen A, it went to state B. By the way, the reward was 0 on that transition. So let's guess that that happens every time. And then in B I saw 8 times, and 6 out of the 8 went one way to a 1 and then stopped. And 2 out of the, no, I saw it 8 times. 6 out of the 8 went to a 1, and 2 out of the 8 went to a 0. So I'm building this in my head. Okay, this is like, and this has a name. This is called the maximum likelihood model of the MDP. It just means what you'd get by counting. Say how often do you go from here, turn those into probabilities. Okay, this is the maximum likelihood model of the underlying Markov process. And then if you take this model and you solve it, if this is the true world, then the true value is 3/4. Okay? And so this is the general phenomenon of what TD does if you present a training set over and over again to it. It gets the answer that you would get if you collected all the data, made a maximum likelihood model of the world, and then solved that model with dynamic programming or with any method. The true solution if that model was the reality. Okay? And so that's, well, that's why TD can be faster, can be better, because it's using this Markov property that it's saying, oh, and I've gotten to B, I know B is a Markov state. And whereas Monte Carlo just says, I don't care about what happened in between, I ended up with getting a 0. Okay, so to summarize that, the prediction that best matches the training data is the Monte Carlo estimate. Best matches the training data. Remember the training data? Okay? And if you saw A once, and it ended up with a 0. So if you want to match the training data, the right prediction is the value of A is 0. That is the prediction that will best match the data. Okay? Now, of course, I want to tell you, we don't want to match the data. we don't want to minimize the mean square error on the training set. Weird, huh? I mean, it seems like we should want to minimize the mean square error on the training set. And that's why I've gone through at some length this example with you guys. So I want you to have some intuition of why we don't want to minimize the mean square error on the training set. So what can I offer you if I can't offer you minimizing the mean square error on the training set? It's going to be minimizing the mean square error on future experience. Because we don't really care about the training set, past experience. We care about the future. And so we think, if we believe we have real states here, we would think that the estimate, the value of A is 3/4, will actually be a better match to future data. Okay? If we get a new experience with state A, it's probably going to end in a 1, 3/4 chance of being in a 1. Okay, so it's interesting. Now we have to really distinguish between minimizing error on the training set, minimizing error on the future. These are different things. And TD can be faster because it can take advantage of the state property and match future experience better. Now, even as I said that, you may be able to get immediately a sense of a possible limitation of TD methods. As I said, they're going to take advantage of the state property that I know when I get to B, it doesn't matter how I got to B. But in real life, you don't normally have complete state knowledge. You have incomplete state knowledge. If anytime you're using function approximation, here we're just using discrete states. And anytime you're using function approximation, you're going to have imperfect knowledge, imperfect state information. And so in the end, it's going to be a mix. It's going to be a question which is going to win in practice. But in the end, it's going to be TD that wins in practice, I'm thinking. Okay? In the end, Ed. Okay. Okay, so, yeah.
Can I make a question?
Good. Good time for questions.
So usually when you introduce the problem originally in the beginning of your talk, you use V to predict the return, right?
Yes.
The reward. But in this example, V is predicting the reward of each state.
No, V is still predicting the sum of the rewards from the state to the end. And So you remember the example was A is followed by a 0, is followed by B, is followed by another 0, is followed by termination. So we're still trying to predict the cumulative reward until the end. Okay? Thank you for clarifying that. Question?
Yes, thank you for this possible disadvantage that if you are so fitting the Markov model,
Yeah.
that it can be a drawback. And coming back to the initial comparison of this initial idea that to be scalable, you really have this computing to be non-local. Yes?
Yes.
You said that. And then I was thinking that, I mean, if you have an explicit representation of the states,
Yes?
then the memory overhead of MC is linear. Because you have the states there, you can put just a number of them and remember who they are. Yes, it's linear. And of course, the computation is not localized. That's okay. But then if you have an implicit representation, where you point to when you said about function, having a function approximation, then of course in this case TD is not going to be sublinear. Yes, depending on the size of the representation of the function. But then the updating this function, this compact representation can be expensive. So there's something there about the space and the locality that is like it's hard to have both of them.
So let's think that through. So let's assume that instead of having a table lookup, this is all table lookup, but instead of that we have a complicated neural network, right? And so then when we get a new error, we have to backpropagate through the network. We have to do somewhat expensive computation, but it's not. Should we consider that expensive? I'm going to say no, because even the backpropagation of one error, backpropagation to the network, that complexity is the same. It's the same order as a forward pass to the network. So we already spent we had to make the forward pass in order to get the prediction, and so there's an equivalent complexity to do the update. So even though it's a bunch of weights, we should consider that cheap. Okay. Okay. It's linear in the size of the network. Good. Good. Any other questions? Good. Okay, so so I've just done one-step methods, tabular methods, model-free methods. All of these qualifiers can be generalized. But even here in this simplest case, one-step method meaning we're looking from one step to the next step rather than one step to 5 steps ahead like in AC3. But we can see the basic ideas. And it's tabular. Tabular is easy to think about, but all the ideas really do generalize to the network case. Complicated function approximator. We've seen the basic things is that we're going to bootstrap and sample, combine aspect of dynamic programming Monte Carlo. The TD methods are computationally congenial, just a little bit of work on each step, and you don't have to wait until the end and then do a whole bunch of work. And if the world is truly Markov, then TD methods are faster. That's what we see. And it has to do with the past data versus the future data. Now, before I go into a somewhat new thing, I'd like to also try to summarize where we are in terms of pictorially. Okay? What today we've talked about contrasting TD method, a one-step TD method, which is like, this little picture is what I use to summarize the method. The thing at the top is the thing updating it. And this says I go ahead one action and one next state, and then I use my estimate here to improve this guy. So this is like a picture of the algorithm. And the same kind of picture for Monte Carlo is you want to improve the estimate of this guy's value. You go ahead one state, one action state, all the way to the end, and you see the final outcome, and then you back all that up. Okay, so, and this is like a dimension. You can occupy intermediate methods. You can do two-step methods, three-step methods, four-step methods, five-step methods. This is like an infinite step method where you go all the way to the end of the episode. And then there's the parameter lambda you might have heard about in TD lambda, the eligibility trace parameter. It's really a bootstrapping parameter. It determines it's not the number of steps, but it's analogous to the number of steps. So this is really a dimension, and we can occupy any point along this dimension. Okay? And now there's a second dimension, which is, are we going to use planning? Okay, are we going to use knowledge of the model of the world? Okay, dynamic programming. Dynamic programming is this corner. It means we're still going to do one-step methods. In dynamic programming, you only had one step. And use your estimates at one step, look ahead into the future. Okay, and so that's moving along the top here. It says keep the short backups, one-step backups, but instead of doing a sample, do all the possibilities. And that's dynamic programming. And then there's a fourth corner where the analogous of Monte Carlo, but with planning, is like exhaustive search. You consider all the possibilities all the way to the end. And so we can get these four corners as classic methods, and then we can occupy the area in between them. And that's kind of a big space of reinforcement learning methods. Although it's certainly not the whole space. Okay, now where shall we go next? I don't have time to present all that I wanted to say, but let me just sort of, we've done a good group here. I can almost sort of wrap up and talk about the future from here. But let me just tell you some of the things that if we had more time, we might talk about. Okay? First, we would talk about estimating, instead of state values, we talked about estimating action values, because as you know, really for control, you want to do action values. And it's not that different. You would just estimate q pi instead of v pi. And it's going to be lowercase, because this is the true value function, q pi. And you would estimate it with an action value estimate. Since it's just tabular, I can say big Q of SA for the actual state and action encountered. And then this update is essentially the TD update. It's just done on state action pairs rather than on states. Right? This is still a TD error. This is my original estimate. This is the estimate for the next state. And this is the SARSA algorithm. And that's quite straightforward. And so the SARSA algorithm ends up being that rule, that update done over and over again. And some examples. Q-learning. Q-learning is almost the same. The rule is, we're updating a state action value. The new one is the old one plus the step size times the TD error. But the TD error is a little bit different. The TD error, we're comparing our original estimate to next reward plus something of the next state, but it's the max of our possible actions at the next state. That's Q-learning. I like to draw this picture. This is its picture. The picture says, I'm updating a state action pair, all the possible estimated action values, take the max of them. That's this part of the rule, right? Max over all possible A. And then I back up the max to improve the estimate of this guy at the top. That's Q-learning. It's a TD algorithm with that particular target. And this is a nice example. Cliff walking is a nice example comparing SARSA and Q-learning. SARSA is an on-policy method. Q-learning is an off-policy method. And we see that actually here the y-axis or the y-axis is reward per episode. SARSA will actually work out better. I don't have time to explain this example. I didn't want to do something that you guys didn't really understand. Better to skip over it. Okay, here's one sort of new algorithm, expected SARSA. Expected SARSA, if we look at the picture, right? In Q-learning, you take all these possible things you might do, and you take the best of them. Take the max. The arc means max. And if you don't have an arc, then it means expectation. Okay? So in expected SARSA, you don't take the best of the things you might do. You take the expectation based on how you would actually do them according to your policy. So here we are. we're summing over all the things we might do. How likely are we to do it under our policy? Which we know. We know our policy. We know how likely we are. Like maybe it's epsilon greedy. And we take the expectation, the action value times our likelihood of doing that action, and we back up that. Okay? And that's arguably an improved version of SARSA. And it can also be made an off-policy version of SARSA. And there are some other novelties. You can do an off-policy version of expected SARSA. Now, I've used the word off-policy a couple times without explaining it. I'm sorry about that, but off-policy means that you're learning about a policy that's different than the one you're following. Okay? And on-policy means you're learning about the same policy as the one you're following, the same one that's generating the data. So the way to remember it is that on-policy is almost one policy. And in on-policy methods, there is only one policy. It's a policy you're doing, it's a policy you're learning about. But very often, these want to be different. Like, you want to do something that is more exploratory. And you might want to learn the optimal policy. Okay, so if you're going to learn the optimal policy, but you're going to actually get your data in an exploratory way, which is not going to be optimal, then you have two policies. Okay, and then you're in the realm of off-policy learning. Q-learning does this, but off-policy learning is theoretically more difficult and more challenging for our methods. Okay? That's off-policy. Okay, so basically I just extended these things to control. Okay, now, and we've seen some methods that can do the on-policy case and the off-policy case. We didn't talk about double Q-learning. Okay, so but I've talked a lot about do we want to use Monte Carlo or do we want to use TD? Okay, and there's a sense in which we don't have to choose, because if you use an algorithm like, if you use TD, you can parametrically vary lambda or vary the height of your backups to give you any intermediate point between one-step TD and Monte Carlo. You can get both. And a convenient way of doing this is with the parameter lambda, the bootstrapping parameter, which I didn't really talk about, but it is a way to vary parametrically between TD and Monte Carlo. So if lambda equals 0, which is the left side of all these graphs, that's pure TD, pure bootstrapping. Okay? And if lambda is 1, that means you're not doing any bootstrapping. It's Monte Carlo. Okay? Okay, so now all these graphs have lambda across the bottom, so it's basically like this, to pure to no bootstrapping. And they all have a measure of performance on the top, where in all cases lower is better. Okay, so it's like a mountain car, and you want to have few steps to get to the top of the hill. Okay, so and what you see looking at this is that performance depends on lambda. This is the random walk, and it's actually not best at lambda equals 0. Pure TD is not the best. You can do better if you do some amount of TD intermediate between pure TD and Monte Carlo. But if you go all the way to lambda equals 1, then things get really bad. That's like the worst case in general, and that's the pattern. Lambda equals 0 is Monte Carlo, and Monte Carlo has really high variance, and it has to be ruled out. It's not very happy if you are committed to Monte Carlo. Now you can do TD and say, oh, I can pick any step in between. That's what you want to have this facility of doing some bootstrapping. And that's sort of some evidence for that, even though this is old data. I think, like Peter would agree that Monte Carlo is not really an efficient strategy to do it in a pure way. Okay, now I want to give one slide also before taking questions on the linear case, a case with real function approximation. I'm not going to go to nonlinear networks, but I want to go to something which you talk somewhat theoretically about, which is the linear case. So suppose we're doing linear function approximation. Linear function approximation means that our estimated value is formed as an inner product between a parameter, a weight vector and a feature vector. Okay, so feature vectors are phi. Phi for feature. Phi of t is our feature vector for the state at time t. And the parameter vector is theta. And that might think about it as the weights of your network. This is a linear network. Okay, so we take the inner product, and so this transpose thing means the inner product. So theta inner product with phi is our estimated value of state t. It's the estimated value of the state at time t because this is the feature vector for the state at time t. Okay, so this is our estimated value of time t. This is our estimated value at time t plus 1. So this really is a TD error. And this is a TD rule. The TD rule is that the parameters are the old parameters plus step size times our TD error, and this then you need the gradient. In general nonlinear cases, this would be a gradient of the prediction with respect to the parameters. In the linear case, it's just the feature vector phi, excuse me. Okay, so that rule should be fairly familiar to you now. It's just a TD rule using a stochastic gradient descent. Lots could be said about that, but that's the standard linear TD0. And if you look at this, you can of course write it like this. You could take the phi and carry it inside. Here it's there, and you carry it inside here with a little some transposey stuff. You can write it like that. And this is a vector. If you take the expectation, we're going to take the expectation. Okay, so in expectation, the new feature vector is the old one plus a step size. And this thing in expectation, what is it? Okay, well, I'm just going to make some names for it. This thing is a vector, and this thing is a matrix times theta. Okay, so B is what I'm going to call that vector. So that vector B is just the expected value of this thing. It is a well-defined vector. You don't know it, but it's there. And this thing is a matrix because it's an outer product of the feature vector with a change in the feature vectors. So the expectation of that matrix is what I'm going to call A. So that means let's write the whole expectation like this. And now I'm interested in what happens at the fixed point. Where will this settle in expectation? Where will it converge? Where will the expected update be 0? Well, the expected update is basically this part. So I want to know when is that 0? Well, that's going to be 0 when B equals A theta. Or when B minus A theta is 0. Okay? And that theta, that's a special theta for which this is true. So B minus A theta equals 0. I'm going to call that theta TD because it's the fixed point that TD converges to. The linear TD converges to. Okay? And then you can just compute it. So B is A times theta, and so you have to take the inverse of A, and you get the TD fixed point is the A inverse B, and which by the way is a key to another algorithm. Least squares algorithm says estimate A directly, even though it's a matrix. Take its inverse and also estimate B directly, and then multiply them together to get, that's how the least squares TD works. Okay, but this is a way of computing what the algorithm converges to, and then you can say something theoretical about it. This is our guarantee that we get, that the mean square value error, a measure of how off the values are, is bounded by an expansion times the mean square value error of the best theta. So this means that we don't find the best theta, okay? But we do get an expansion of it. Anyways, that's what the theory would look like if we had more time to talk about it. I just want to mention quickly some of the frontiers, some things that people are working on now. Off-policy prediction is a big area people are working on, trying to generalize to the off-policy case. Also, we'd like to talk about have some theory for the case of nonlinear function approximation. There's just a little bit of that. There's also very little convergence theory for control methods, period. And I think Chaba, maybe we'll talk about that tomorrow. And we also like to say things beyond convergence. We like to, how well can you do in a finite amount of time? How fast do you converge? Now, when you combine TDE with deep learning, a lot of different issues come up, and I think there's just a lot of uncertainty. Do we really need a replay buffer? So that one of the folk theorems is that, oh, especially you have instability and correlation, quote correlation, so we need this thing called the replay buffer. But I think it's really, there's lots of questions about what happens when we combine TDE with deep learning. And finally, the idea of predicting things other than reward. Remember I started with that. We might want to, TDE is a general prediction method, multi-step prediction methods. We want to use it to predict other things. And in particular, we want to learn a model of the world. So in conclusion, I guess what I want to say is something like this. The TDE learning is a uniquely important kind of learning. Maybe it's ubiquitous. We're always going to be using it. And I think this may be true. It's a hypothesis. So anyway, it's learning to predict, which is perhaps the only scalable kind of learning. It's a kind of learning that's specialized for general multi-step prediction, which may be the key to perception, modeling the world, the meaning of our knowledge. Its key idea is to take advantage of the state property, which can make it fast and efficient, but can also make it asymptotically biased. And its other key claim to fame is that it's computationally cheap, congenial, and we're only beginning to explore different ways of using it for things other than reward. Thank you very much.